Good morning, everyone. I am Dr. Ewa Ibrahim Inusa. I am here. I will be taking you Physics 121, Electricity, Magnetism, and Modern Physics, alongside Dr. Abdul Mumini Zubeiru Loko. Two of us are going to be taking Physics 121, which is titled Electricity, Magnetism, and Modern Physics. By the title, you can see that the course has three different areas. First is electricity, second is magnetism, and the third part is modern physics. Electricity part is going to be taken by Dr. Abdulmumini Zubeiru Loko. I will be taking modern physics, and then the magnetism is going to be taken by the two of us. We're going to share the magnetism in two different parts where everybody will take half of magnetism. Let us look at the course contents for this course. The course contents are as follows: electrical charge, Coulomb's law, electric field, electrostatic potential. That forms the first topic for this course. 2, we have energy in an electric field, capacitors, dielectrics. 3, we have electric current, potential difference, and electromotive force, Ohm's law. 4, we have potentiometer, meter bridge, Wheatstone bridge. 5, we have magnetic effects of current, permanent magnetism, Earth's magnetic field. 6, we have Faraday's law of induction, generators and electric motors. 7, we have alternating current. 8, we have Maxwell's equations. 9, we have structure of the atom. 10, we have radioactivity. 11, we have X-ray and its application in life sciences. 12, we have nuclear energy. These are the course contents for this course. In the contents, you will see that we have the electricity part we have the magnetism part, and lastly, the modern physics part. For today's class, I'll be speaking on Maxwell's equations. Maxwell's equations are a set of 4 fundamental equations that describe the behavior of electric and magnetic fields. They are formulated by the Scottish physicist James Clerk Maxwell in the 19th century and are one of the cornerstones of classical electrodynamics. So from what I'm saying, it means that Maxwell's equations are fundamental equations that constitute what we call classical electrodynamics in physics. Maxwell was the first person in physics to calculate the speed of propagation of electromagnetic waves, which was the same as the speed of light, and concluded that EM, that is electromagnetic waves, and visible light are similar. This discovery was made by Maxwell. This set of partial equations, because the Maxwell's equations are a form of partial differential equations. They are a set of partial differential equations that form the foundation of classical electrodynamics, electric circuits, and classical optics, along with Lorentz force law. These fields highlight modern communication and electrical technologies. The 4 equations that we are talking about are as follows. 1, we have Gauss' law for electricity. This equation relates the electric flux through a closed surface to the total electric charge enclosed within that surface, and it is given by closed integral of E, which is the electric field, dot dA equal to 1 over epsilon naught integral of rho dV. The definitions of these letters are as follows. E is the electric field, dA is an infinitesimal area vector. Epsilon naught is the permittivity of free space, which is a constant. Rho is the charge density, which is also a constant. And the integrals are taken over the closed surface and the volume enclosed, respectively. From slide 1, from the previous slide, where this equation was stated, you will see, you agree with me that there is a term there that says electric flux. Electric flux is simply the electric lines of force that intersect over a certain area. And these electric lines of force are not things that we can see with our naked eyes. They are things that we cannot see. And so, anytime they intersect or pass through a certain area, we refer to them as electric flux. The next equation of Maxwell is the Gauss law for magnetism. You can see that just like the cause is electricity, magnetism, and then we have another term that is electromagnetism. That is the bringing together of electricity and magnetism. And you can see that Maxwell's equations is talking about electricity and is talking about magnetism as well. The first one is about electricity, and this one is now about magnetism. This equation states that there is no magnetic monopoles, and the magnetic field lines always form closed loops. It is given by, closed loop is something in the form of a circle, but not really a circle once it starts and ends at that particular point. If you draw something, take for instance, you draw something like this, even though it's not a cycle, but it begins from this point and then it's ending on that point. It means it is closed. It is not open at any end. That's what we refer to as closed loop. And the equation is given as the closed integral B dot dA is equal to 0. This is the second Maxwell's equation, where B is the magnetic field. 3, we have Faraday's law of electromagnetic induction. This equation describes the generation of an electromotive force, which is referred to as EMF, in a closed loop, where due to a changing magnetic field. It is given by closed integral of E dot dL is equal to minus d phi dt, where E is the electric field, dL is an infinitesimal line element. Very small line element, that is what we mean by that infinitesimal, very small infinitesimal line element. D phi dt is the rate of change of magnetic flux through the loop. The rate of change of magnetic flux through the closed loop is what we refer to as d phi dt, and the integral is taken over the entire loop, just like this loop is, we are taking an integral over the whole loop. It's not leaving any part of the loop, but it's over the entire loop. Ampere's circuital law. This equation relates the circulation of the magnetic field around a closed loop to the sum of the current passing through the loop and the rate of change of electric flux through the loop. It is given by closed integral of B dot dl is equal to mu naught into I plus epsilon naught d phi e dt, where B is again the magnetic flux field, B is a magnetic field, dl is an infinitesimal line element, I is the total current passing through the loop, epsilon naught is the permittivity of free space, mu naught is the permeability of free space, d phi e dt is the rate of change of electric flux through the loop, and the integral is taken again over the entire loop. These four equations, together with 13 additional relations, such as the equation for the Lorentz force, form the foundation of classical electrodynamics and describe the complete behavior of electric and magnetic fields. They have profound implications for various areas of physics and engineering, including the study of optics, electromagnetic waves, and the behavior of electric circuits. These equations can also be written in the following form. The first one can be written as divergence of D is equal to rho. Divergence 2, the second one can be written as divergence of B is equal to 0. The third one can be written as curl E is equal to minus dB dt. And 4, curl H is equal to dd dt plus J. So this is another form of writing the four Maxwell's equations. If you write them in this form, you are also very correct. And just as this course is, it is an introductory part of physics, because it is acting as introductory electricity, introductory magnetism, and introductory modern physics. The three come together to form this course. And so whatever we are going to be doing here is going to be on the peripheral side. It's going to be on the elementary side. The introductory parts only will be touched. As you are going higher in your higher levels, more of the details will now be revealed. Because at this point, part 1 of physics, all you need to know are just the introductory parts of physics, which are not quite far from what you know from your secondary schools. Most of the things we are going to be dealing with here are some of those things that you are already a bit familiar with from your secondary school physics, if you had physics teachers that were up and doing. And so you won't be seeing anything far from what you know from your secondary schools. But as you go to 200, you will start seeing new things. When you get to 300, you will see entirely things that maybe you have not seen before. Or maybe you are seeing them. Some of these things we are doing now are some of the ones that you'll be seeing their advanced form in those higher levels. So this course, just like I said earlier, is an introductory course. And so we are not going to be dwelling into so much details, because doing that can even scare some of you away from physics, and you begin to hear that I want to change to another course, I want to change to another course. So we will deal with strictly with the elementary parts, just like the course contents as stated. And then as you grow higher and higher, and you will now be seeing the details of details and advanced form of this course. So for this class, I think I can call it a day, and I want to say thank you all for attending and listening. Thank you. We meet again in our next class. Have a wonderful day.